Boop. Now we're recording. We're going to do some of this. So I actually did all the work today ahead of time, and I didn't get it wrong. Come on. I know, right? So let's get it wrong now. But it's actually super easy stuff. I think they try to overcomplicate it with all these words. And so let's do some key points. Key points of what we're doing today. We're looking for this thing called a potential function, and this is your formula for it. But what's going to happen is that this is like the finalized formula. What we're having to do is kind of use it backwards. In a way, this gradient, means derivative. So what we're going to actually do is integrate both of these to get like integral of f is kind of equal to little f plus c. This is kind of what we're going to do, and I'll show you when we get there. Very simple. It's just instead of derivative, you do an integral to kind of reverse the process. Cool? There's a little bit more to it, but we'll see it as we go. That's one key thing today. And then, have you seen this before? Have you seen that? Do you know what that's called from Calculus 1? It's been a while. Kinda. This is the fundamental theorem of calculus. Y'all don't remember that. That's fine. That's why they pay me to do this thing. But it means nothing to us. Basically, FDR is equivalent to all these. So like I said earlier, we like this guy. Well, now we got all these others that we could do as well. I don't even think I did a B minus A today. We'll see, though. So some other things that are kind of cool, this conservative stuff will come up eventually. So basically, if you have your integral is equal to 0, it's conservative. Kind of think of it like conservative, like you're conserving energy, right? It's all kind of contained in a certain place. I think of it kind of like a pot that has the water and stuff inside, right? So it's not getting out of it ever. Or you heat it up and it stays inside and it has pressure, but it can't get out, that kind of thing. I don't know. That's physics, is it? Yeah, we're going to move on. It's just physics-y, kind of like the energy is conserved, I guess. And then how do you find that? This is the formula for it. Now, it looks like a lot, but if I split it up into 3 separate mini formulas, you'll see that it's basically just saying if this equals that the whole way down. I did not use this today. I did not use it today, so I don't know if it even comes up on the homework. I assume that it should, but I didn't see it. I don't know. We can go back and check later. Is this okay? I'm just kind of getting the blah blah out the way. And here we go. So it finally says find the potential function. Now they do say potential functions, and I'll show you why. What we need to do is cap f is equal to grad little f, and all I'm going to do is integrate both sides. So my integral of this dude is equal to little f plus c. This is my goal. I'm going to integrate and say plus c. What do I integrate, though? Here, look, integrate. What do I do there? Just integrate it. Come on, I'll wait. And it's like, what's going on, right? It just looks weird. Well, the thing is that if you distribute this, you have 3 separate little vector thingies, right? 3 different components, 3 separate integrals. And what we're going to do now, it's very simple, is I'm going to say 5 times this dude, because that's going to be the first one, dx, because he's in the x component, right? X component. What do you think I would integrate for the y component? Almost 20x. Yep, but very close. You got it. And then, like you said, dy, right? Because that's my y component. Last one, what do I do here? Mm-hmm. 15x, e to the blah. And then what do I put at the end here? Perfect. What we're going to do is do these 3 little integrals and just see what we get. 3 separate little integrals, see what we get. The goal is that we're going to actually, hopefully, get the same thing. Okay? We're hoping that we actually get the same thing because what we're doing is, like, if we took our derivative, we would get this. So if we integrate each of them, we should come back to the original. That's what we're looking for, is the original, what did he start with kind of thing. So when I integrate this in terms of x, what do I do? You just add an x to it. That's kind of funny. And I know in Cal 3 we don't do this very often, but Cal 2, Cal 1, what do we have to put? We don't really do that very often here. But now... Yeah, I know, right? Haven't seen that in a while. Yeah. If I have to integrate this in terms of y, it looks scary, but really the only part is that little dude right there. Okay. There it is. Blah, 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 blah. U sub, you divide by a 4. No, and that's exactly right. If you're taking a derivative, you would say multiply by that number, but because you're integrating, you simply divide by that number. That is actually the entire process, and that way you don't have to go down a whole, scary road. You're just dividing by that little number up there. And then plus c, yeah. Isn't that interesting what we're getting here? That's a 4, by the way. 4 and 20, what does that make? Interesting, right? Let's verify this last guy. What would I divide by this time? There it is. That little 3. And then plus c again. So, if I wanted to know what they have in common, I'm going to write, what do they have in common, all 3 of them? You would say, yeah. They all share that in common. All 3 of them have this thing, right? Is there anything else that one of them has that somebody else doesn't or something? No? So how I go about it is I want to have at least whatever anybody says is part of their answer. Now, I say what's common because that's the first thing we think about, but even if they had a little extra here, I would have to include them as a just in case. And I'll show you that when we come to a new problem. Right now, they all have this guy. So, and one other thing, there it is. They all have a plus C. And that's your final answer. Now, I'm going to flash the answer. Kind of, in a way. Here, there's your answer. See, so we got it. Kind of. Sometimes not so. This time, I would say yes. And here's the thing that's very tiny. We don't really talk about it yet, but we will soon. That C is a CX, kind of. Not derivative in terms of X, but just like you have to label him. Normally, we would just say C1, C2, C3. But this guy is really, he's an X focused. There might be things in there that I don't really know that have Y's and C's. I don't really know. So we'll see. You're correct. These are actually kind of different maybe, but in this case, they are the same. The math was not hard, right? The math's not hard. When we get to something that's a little different, I'll show you why I'm kind of making a big deal about it, okay? I'm making like a for no reason. Okie dokie? You're good? Okay. Keep cruising. Let's do something else. This is not the same problem, but if you scroll down one more, there's another potential function one. I almost want to do this one first because it's the same thing we just did. Is that okay? Okay. So same thing, same idea, but this is only 2. So that's like even easier. So I need to integrate this. And so I'm going to integrate my first one here in terms of x. See what we get. And then I'm going to integrate my second one in terms of the y and see what we get. And I hope that we get the same thing. And if not, that's fine. We kind of work around it, kind of figure out what's going on. I almost want to have this as a you-do. Yeah, let's do that for a minute. Because it's not too hard. So glad y'all are here. Got the whole crew back. And I like this class. As in, I like y'all. Just trying to say it without being too sentimental. It seems too easy, isn't it? But maybe not. If I integrate in terms of x, what would I get? Okay. Let's see. Right, the 2 canceled with the 6. He just did it automatically. But you're good. Yeah. And then I gave you the stare. The Cal 1 stare, the Cal 2 stare. This one, it kind of threw me for a second, but this right here, if we rewrite it, I'm just going to show you how I thought about it, was this guy. Oh, I know. Oh, yeah. That design makes it a little easier because it's only the y. Again, everything else is just a number, kind of. So what do we get then? So you would add 1 to the power, so you would add in the numerator, you get negative parentheses 10 minus 3x squared. And then over, you would have just y. Thank you. I know I'm being so picky today. Well, right, and they were picky back in Cal 1, Cal 2. Yeah. Oh, I know, right, I know. Yeah, I know. So, I wanted them to be the same, and they're not. They're definitely not the same, but they got something that's similar. I feel like they have common elements. Uh-huh. Uh-huh. Yes. If I rewrite this and I distribute my y denominator, so this is my answer for one of them, this is my answer for the other one. They do have some parts that are in common, which is great. That actually kind of tells me that we're doing something right, you know? This guy is not in common. That's okay. We're going to include him anyways, okay? I don't know how to put a good analogy to it, but, okay. Someone is requesting food for lunch, and they say, hey, does everyone like pizza? Yes. And one person says, Henry, right? It's always Henry. Henry says, oh, I want breadsticks. All right, so when I go and buy pizza, do I also buy breadsticks for him? Yeah. But like, even if y'all are all buying pizza, everyone else is cool with pizza. Everyone else is cool with pizza, but Henry wanted breadsticks. I'm still buying breadsticks. So what is my answer? Is actually the pizza and the breadsticks together. And so this is my final answer for what the potential function is. Let me go back and flash the answer. There you go. See, and they just mushed it together. Oh, they don't have a plus C. Look. Oh. I don't know how to explain what they got. I don't know. I wouldn't. No, I think they're just wrong. So, yeah. Anyways, I would say if you add a C and they don't like it, just watch out. Go ahead. There it is. Exactly right. That's the point. So if I were to go and take this and take a derivative in terms of x, that's a d dx. Doesn't look very good. Let me try over again. So yeah, what if... and it's a partial technically, isn't it? Okay, so if I took my derivative in terms of x, technically, then this number goes away. This guy right here, I bring the 2 down and I get a 6x over the y. This guy turns into a 0. This guy turns into a 0. And see how we got back to our original x? And that's the point here. So, and then we do it again for y. If I did this with my y, then I should come back to this guy right here. I'm not going to do that, but you get the idea. Common denominator, blah, 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 whatever. So it's okay. We want, yes, everything in common, but also whatever any other request there is, we want to include them all, just in case. And like you said, because this will just get it canceled out. You're only eating pizza, you don't care about breadsticks, whatever. It's just going to go away anyways. But the guy who wanted breadsticks, we definitely still need it for him. Then it changes everything. Yes. If you didn't want pizza, or you wanted pizza, not breadstick, you don't eat no breadsticks. It's only for Henry. Anyways, so are y'all okay with the concept though? We're integrating, and we're wanting to say whoever we got. Yeah. Okay. It would almost be like not least common multiple, but like greatest common factor kind of thing, I guess. No, I don't know if I even like that. The bigger one is better. The bigger, the more. If somebody says for breadsticks, we put breadsticks in there. Okay, moving on. I just keep doing analogies. All right, back up to this guy. He looks interesting. I mean, if you look at him, kind of hey, go ahead and integrate. But how do I integrate with these three numbers on one integral? Do you see the problem here? There's only one integral symbol, not three. Well, and that's the thing. So in a way, yes, we could try to tackle it that way, but then how do I put these in at the end? That's the problem. I think I could integrate each one of these individually, but I don't know how to find the limits, if that makes sense. And it might be just that easy. I didn't try. What we want to do instead, technically, is replace this with stuff. So it says there's a path. If you know how we've been doing this, that's an R. We're gonna find an R vector, and that's there it is. You got it. That's exactly right. So that's what I'm gonna set this thing up as. My X is going to be I'm going to write it out in English first, from 1 to 8. How that works, like you said, terminal minus initial, I'm going to say the 1 plus 8 minus 1 times t. So the formula is kind of like x naught plus terminal minus initial. I don't know. I don't like that. I'm going to do just i's. Initial, terminal minus initial, and then times t. That's kind of like the formula for it. So that's my x. This is x. So for y, what would I do for y then? Like, what's my initial? Yes. And then what am I adding? 4 minus 1 t. Yep. And then finally for z, what do I start? 3. And then I'm going to do terminal minus initial. It's a little weird. Yep. So this is my initial. This is my terminal. And I'm just going from here to there. But that's my formula in a way. I'm just going to put my numbers in. So again, I have a 1 and 8. So I go 1 plus 8 minus 1. Got a 1 and a 4, a 3 and a negative 2. Yeah? No? Oh, you're okay? Okay. Yeah? You want me to go over again? Here, no, real quick. So, I think the official formula was something. I don't know if I even like this one, but like we always start with our initial point, and we're gonna go out to another point, A and B, I guess, something like that. So I like that better as being A, or yeah, this is an A. So I'm going from A to B, and over a span, this is always going to be t equals 1 second, I guess. Like it's not just a standardized, like I'm just going to call it. It's just a formula, I guess. So I'm going to start with A and go to B. So this is my formula initial, and then that's my slope in a way, right? because I'm saying how much distance did we travel from A to B? That much. And then I say in 1 minute or 1 hour or whatever. Yeah, and I'm using this formula because it's way super easy. I'm purposely doing the simplest thing possible. Because when I first looked at this, I'm like, okay, I need a formula that makes all these things work. It's not the point here. You don't need to make them all work. You need to make one work at a time. And so each one of them now, I'm just going to integrate 0 to 1, and it'll be fine. And that's my goal here for this one, okay? So let me replace it now. I'm going to now say 0 to 1, blah, 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 dt. Like, that's my goal, is I want to say, just make it super easy. And this is kind of like a default kind of... I had to make up something. I'm making it up, and it's super easy. My first initial thoughts were like t for 7. Like 0 to 7 for t, because that's what we would have needed to get to here. But that would have been kind of weird. You know what I mean? Try to keep it easy. Is that okay? Like, just kind of like follow the default blah. And now, yeah. Yeah. Yeah, there's a lot more math. We haven't really, I just wanted to kind of set it up. You're right. So I want to now make it easy formulas, if that's okay. Like 7t plus 1, 3t plus 1, and then this was negative 5t plus 3. So that's my x. I want to find x prime, right? I want to find dx. This is my derivative of this guy. Just take a guess. Just 7. Yeah, it's dt. Okay. Oh, yeah. You want to be technical because I was technical about the plus c.
Oh,
No more technical anymore.
I was thinking that'd be dx dt so that we could replace them in the formula.
100% true. 100% true. What's my y prime here?
That would just be 3.
And then finally?
That would be negative 5.
So these are going to go in right here, here, and here. Those are, like, I say x prime, but I mean dx. I mean dx is dt. That was technical for James. But I'm just, what's the derivative, right? It's going to be a number. So, like, my answer right now, what I want to do is y times 7, x times 3, 3 times negative 5. See how I'm plugging them in directly? Oh, but wait. I can't do this one yet. I still have y's and x's with dt. There it is. We have a formula for that. So here we go. Final formula, I guess you can say. Here we go. So y is going to be this thing. 3t plus 1, and then times the 7. Oh, I didn't put a 1. That would change things. Now times the 7. My x, I have it. 7t plus 1. Ah, man, parentheses and ones. Do y'all ever get that confused? No, Chad. And then the last one, there's nothing to plug in. This is going to be my answer. Whatever that is, that's it. I have to simply replace everything I have with t. So, like, if I go back to the very first original, I can't have a y, so I have to replace it with something with t. I can't have a dx, or replace it with something with t. This is probably not how they want you to do this problem. I'm just trying to do it the most, like, straightforward, brute force method. And for me, that's just, like, I guess plug it in. Substitute. All right, what do we do now? Thank you. In chapter 16, it's Desmos. No, I did it by hand earlier. True. Yeah, it is a little easier. Let's go to Desmos graphing. And Desmos graphing. And I'm just going to integrate this thing real quick. 0 to 1, default answer stuff.
The answer would be 17.
You already got the answer?
I think so. I'll try to beat you to prove a point.
Fine. And you laugh at me about it. Yeah.
Hey, rounding up, Chad, rounding up.
Sure. And yeah, the answer is 16. I did it by hand also. It's not that bad. You round up. For safety. You should know that now. Oh, okay. So zooming out though, are y'all seeing what I was kind of getting at? A little bit? Yeah? Plugging it in. Is there another way to do this? Yes. I don't really know what that would be. I think they use the potential function or something, but it's not a big deal. This one is a plug it in just like we always normally do. I think the only confusing part is that we had to make an R that normally we have it already given. So we just had to make it from this formula thingy. Okay, cool. I think I broke something just now. Okay, there we go. We're good. Scrolling? Okay. Awesome. And that was it. Yay! We can go home. No, I'm just joking. No. So Green's theorem. In the past, when I've done Green's theorem, it's the start of the more intense math. What I found is that it's very simple. Green's theorem is designed to make it easy. Okay, so as we go forward, you're going to say Green's theorem good, even though you might think that Green's theorem is a little bit more right now. Okay, because it gets worse. But it's Green's theorem is the first of the theorems that we're going to be learning, and this one's the easy one. I think I put a word here. If you don't mind for a second, I'm going to go back to my instructor side. Yeah, okay, I called that one curl. So this one here, this one's called curl of f, and I think they do like dot k vector or something. But if they say curl, this is the formula, and they already have divergence here. These are pretty important ones. I can't remember if I used divergence yet, but we will use it later. There's divergence theorem is the last section, and it is like all about that thing, which you're going to be happy about because it's an easy formula. Anyways, so we got this guy. Curl. Cool with curl? Okay, I just wrote curl. No, what's up? Exactly. It's the insides of that other stuff. And so as I scroll down, you'll see a lot more of the same thing. This right here is my FDR yet again. Okay, so FDR, we can use this formula on the inside kind of thing. This is the other guy. And he uses the divergence. We'll see that as we keep going. Again, this is FDR. And then we got all this cool stuff here. This is what we had. This is now what we have. So this is the greens. Compare real quick. Compare. This is what we had. And this is what we have. I'm getting tangled here. What would be different? Just give me some things that are a little bit different.
My first thing inside subtracts rather than adds.
Okay.
And then it also deals with the derivatives rather than the functions themselves.
Okay. Okay, good. Yeah. There it is. That's the trick. We went from a single to a double, and that's Green's theorem. That's the key. That's the trick. That's the reason why we're doing it. Because single integrals mean dt. Double integrals mean dA. And so what we could do now is integrate over an area, which, guess what, we've been doing for months. Same thing with this guy. We've already seen him, and then a different formula. What I'm going to have to do is just kind of remind you when they ask for something that we'll just kind of go back to which formula we need. Cool? Okay, so let's do this. It says, what's up? Yeah.
To clarify, people who weren't here yesterday, our last week,
Thanks for asking again. So they mean it's like a full circulation. So when they have a thing here, they're saying they're going around a full circle thing. So it might be like a square box, and then it kind of does this. But as long as you get back to the same original point, yeah. And a lot of times, what happens is if it's conservative, it's equal to 0. So I'll say it one more time. If you have to guess on something, if you have to guess on something here in chapter 16, the answer could be 0. Hmm? Yeah, if you're guessing, don't guess 1, don't guess 2, don't guess pi. Okay, maybe pi, but but 0 is a really good guess because again, if it's conservative equals 0, we're done. Yeah,
It even has a 0 in its symbol.
yeah, there it is. It's saying it could be 0. It could be. Okay, so curl, I have, and it says .k. I think that's just them trying to go with a 2-dimensional version. But rather, we're just trying to find curl. Let's go back to the formula. Curl is that dude right there. So I'm going to rewrite it. We got dn dx minus dm dy. But another version is with the Newtonian version versus the Leibniz version. We're just finding partial derivatives. Now again, remember that M comes first in the alphabet, then N. M, N, O, P, Q, R, S. Okay, whatever. So this is the one that we're going to do in terms of X. And then this guy we're going to do in terms of Y. Yeah? See how it's flipped? Yeah? Okay, so let's do the first one. If I need to take a derivative in terms of X, what would I get? Can I do something silly instead for a second?
Sure.
Can I say that's my original for just a second and do this? I know this is going to be kind of weird. I'm doing some weird notation. So yeah, what's my derivative in terms of X is, well, the same. It doesn't change. But see how I have a little sub X right there? I'm saying derivative in terms of X. Yeah. Well, I mean, isn't that what we normally do? We say F sub X, F sub Y.
Yeah, I just never see it.
Well, that's why I wanted to show you. Yeah. Yeah, I know. All this kind of weird notation he's doing. Just throw some math up there, looks fine. Especially in linear. Blah, 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 blah. It looks great. Therefore, it's done. Yeah. So, this guy right here, derivative in terms of y. What would I get? Not James. Sorry. 1/7 x e to the 7y. Because again, wait. Derivative. Okay, cool. I was going along with you for a minute there. Okay, back to James. No.
I actually was about to say what he said.
Yeah, me too. We're so used to integral. Yeah. Yep. I believe that we're done. And I'm going to just verify. We're going to flash the answer. Let me go real quick. And there we go. We got it. That was it. Very, very straightforward, very easy. The problem with curl, at least in the WebAssign class, is that they do it for 3-dimensionals instead of 2-dimensionals, which is always a cross product of derivatives. And it gets really nasty. Anyways, not here, not today. Not yet. Isn't that so nice of us? Yay for MyMathLab pilots. Good though? Good. Okay, cool. So I have to remind you about these formulas, okay? So flux and circulation. Let's go back up to the top and see which one they're talking about, okay? Right here, flux is this dude, and circulation is this guy. So I'm going to rewrite it down there, okay? This m dx, whatever thing we're doing, okay? So nx, here we go. So my flux is the bottom one. It's double integral of mx plus ny dA. And this one is the nx minus my dA. Let me just verify. Hold on. I know I'm going to come right back. Hold on. Let me verify. Circulation. Yep. Okay. Okay. Yeah, we got it. In a way, what I'm doing, I'm showing you, is I'm decoding it. I mean, go back up to those formulas, and it looks like a lot of right? Yes, it does. Thank you for the agreement. There's so much going on in the formulas. It's like, I don't even know where to get started. Well, this is the kind of quick version. And I'm doing it Newtonian so that you can see I'm just saying, oh, derivative. Oh, derivative. Right, just like what we did a second ago. Yep, nx, correct. Nx. Awesome. So I guess one at a time. Here we go. I want to find out what the inside is to begin with. So this is m, this is n. What's my derivative in terms of x? Sweet. Then plus sign. N in terms of y? Beautiful. And I'll worry about the integral limits in a minute. I just want to make sure that I get it ready. For the second one, n in terms of x. Yep. Very good. Minus, and then m in terms of y. Beautiful. You got it. Okay, I want to pause. I want to pause on this guy. Is it different? See something odd in here, right? Kind of weird. What do you see? That's all. So this does not always happen. The next problem will not be like this. But if you see something like the signs are flipped, you'll get one answer. You just make it negative. Right? On this problem. Okay? On this problem. Yeah. So that's nice of them that, well, we only have to do one integral essentially. But it's still not always like that. Cool? So you get to choose, top or bottom. Which one would you rather me do? Because obviously they're the same answer essentially. So top or bottom? Top one, let's do it. So I want double integral of this guy here. And I need to do like dx dy or dy dx or something like that. It's up to you.
Well, I'm thinking if y goes from 0 to x, then x goes from
Right. This right here is telling you what the region is. So let's draw a nice little picture for this. So y, oh, let me get a different color here. We got, first off, y equals 0. I got x equals 3. And then I got y equals x. So they should meet up here at 3, 3. And like basically they want the inside there. It's a little triangle, which is nice. If I'm wanting to do what I normally do, at least, is dy dx, because it makes more sense for me. What y would I have for the top? What do I say is for the top? And for the bottom, y equals? Cool. See, I'm like, they have a y equals 0 and a y equals x, so I could just plug those directly in, right? Pretty straightforward there. Top and bottom. But now I have to go for x. Left and right. Where would I start? Where would I end? Yeah, I'm starting here at 0. I'm going all the way to 3, and I'm done. That should do it. So if I get this answer for the top, I'm just going to say negative and then get the bottom. That'll be my goal. Okay. Are we doing this together? Oh, okay. So if I integrate this in terms of y, what would I get for this first term? I like that. And then for this guy? Correct. The 2 in the bottom already cancels the 8. Yeah, exactly. From 0 to x. plug in an x, and we basically get like a squared and a squared. Oops, I'm already messing up again. But when I plug in a 0, you get nothing. So yeah, ignore that, I guess. Cool. This looks kind of interesting. What's actually on the inside? Yeah, exactly. You got it. Well, that makes things easier. We like that. So when I integrate, perfect. 0 go away. The 3's right here. I think since there's 27 divided by 3, I'll get like a 9. And 9 times 2 is 18. And again, remember that was on my top. That's my first answer here. So what's my bottom one is now? Perfect. Yep, because I just made it negative in this very one single particular case. Okay, the next problem we do is not the same because it just so happens that this one is funny like that. That's okay. So I warn you again and again and again. So in the end, not too bad. The thing that's like the most jarring is that formula. At the very beginning, I need to know what formula to put where. If it wasn't so clear, well, it's not so clear. If I didn't make it so clear, it would be kind of like, well, which formula do I use, which and where, you know? I think we can all do a double integral. So cool. Any questions? So we're about to do the last one of the day, essentially. That's about all we get around here. We get the one that I did not finish. Yeah.
So what I'm hearing is once we set it up, we use Desmos.
Oh, that's a great idea, actually. Oh, look at that. You're right, because I was, you know what? That's so silly of me. All right, guys, let's keep doing it by hand when I could have just done Desmos. Man, y'all got to tell me that. You got to remind me that. Okay, so I need to use flux circulation, okay? So there's 2 different formulas. You're going to remind me, for flux, double integral of what?
Wouldn't that be mx plus ny?
Okay. And so then this guy would be?
The double integral of nx minus ny.
Okay. As soon as we have that, I think we should be better off. And you can see, of course, that we have an m, and we have an n. So we can find these things. In fact, you know what I'm going to do? I'm going to have y'all do that. And I want you to try to get the limits. Now, I don't want you to actually do the integral because we can just use Desmos now. But I want to see what you come up with the limits and the inside. Like, set it all up, ready for Desmos. This is the last one of the day for sure. Kind of happy and sad at the same time here. They're only doing 2 dimensions. Which is okay. But then we're missing around all those 3-dimensional things. Does it make you sad? Yeah. Yes, you do. Okay. Good. 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 Okay. I wasn't that fast. But I do have to say I did get it right. Without Desmos. I totally forgot about Desmos this morning, so that was totally my bad there.
To be fair, so far with these integrals, they don't seem to be too crazy.
The idea, at least in this section, is that Green's theorem makes it easy. Technically.
Yeah.
Like, in a way, look at what we have here and try to find time for that. And that's the problem. If I had to do it like FDR, I'd have to do time formulas, and it just gets weedy.
I was thinking for our integral, like really start and stop moving from the 0 to 1 distance, like that gets us up there.
Sure, but then you have to come back. Right? 0 to 1. But then you have to come back. See what I mean? And then you need a formula for that. So would you then go from 1 to 2, but now a new path? Yeah, that's the point here, is that we're trying to make it easy by just saying, oh, well, I can find the area of that. I've been doing it since Cal 1. Kind of. Double integral, been doing it since Cal 1. What did y'all come up with for the inside? Minus 5 over 2 y squared. dA. Yes, confirm. Uh-oh, not confirm. Well, let me verify. So m in terms of x would be the 2. Oh yeah, we're doing a derivative. So I think you went the other way. You did an integral. It's okay. I do the same thing. Okay, let's go back. So yeah, derivative in terms of x, 2y. Anything right here? That would go to 0, wouldn't it? Okay. And then plus, and then now n in terms of y. Mm-hmm. I do the same thing. It's okay.
Earlier, all of us were saying, "Oh, you're taking
Divide by 7.
we gotta throw in fraction.
Yeah.
Fraction.
Oh yeah. I know. Yeah, we're going back and forth between our derivatives and integrals so much now.
So there's such a similar idea.
Correct.
It's kind of hard though.
Oh yeah. Oh yeah. I know. It's like, it is kind of funny. We're doing integrals of derivatives. So I mean, we're doing both actually. Kind of funny. What would be the inside for the bottom one? Mm-hmm. 2x. And then very good. Yes, that guy right here would be 10y, like you said? No, yeah, 10y. Right? Okay, good. Yeah. Very good. Good job. Okay, well now we need the limits, and the limits should be the same for both of them, so, which is good, but you can see that they're not like negatives of one another anymore, right? It's like you actually do have to find both separately, but the limits should be the same. So let's try to figure that out, unless you already did. What would you put for the top and bottom right here? Very good. I'm assuming then you did dy dx. Very good. So yes, on the bottom we have x squared, and then on the top I got y squared, but it doesn't fit. It doesn't fit because we need a y. So instead, you square root both sides. Or exactly. So then we got a square root x. And then what was my x values? Yes. Yep, 0 to 1. That's it right there. You got it. And so the same thing for this guy as well. 0 to 1. X squared is on the bottom. Square root of x is on the top of all this mess. And then we... Yay! It's like we're keeping this company alive here at CTC. It's kind of funny. I'm sure many other schools are using Desmos.
Well, I mean, it's a really nice calculator and it's free for anyone to use, so I don't know why people wouldn't.
True that. True that. Yeah, for our online classes, we're going away from choosing your own handheld calculator to like only Desmos required kind of thing. Because it's, well, you can't cheat with it, honestly. You're always looking at the screen whenever we're doing the recorded proctoring stuff. See how we got different answers? That's a good thing. And let me go flash the answer. And you can see I did it all by hand. Oh, wait, that was the other problem. I did it all by hand, except for I didn't do the bottom part. I only did the first one and said, I'm bored. Yeah, and then I didn't do the others. So, oh, wrong one. This one. There we go. Cool, cool. I don't have enough time for the next one. I think we did a lot. Is this okay? Double integrals of derivatives. It's great. Another day in calculus land. Cool. Thank you, guys.